business. How's the homework going for you guys? Okay. Do you have any finals canceled or anything? No. Yeah, I don't really know. It's gonna be weird. Hello. Hello, testing, mic, nice. If you can hear me, I just want to make sure everything's working. All right, we're in business. Thanks. Thanks, Javier. Usually I give a challenge problem for people that show up and don't want to listen to me, but I don't know why anyone would be tuning into a live feed if they didn't want to listen to me. So, oh, well, keep the tradition alive. Okay, on my screen, it's backwards. Can you confirm that it's not backwards for you? I feel like an old man. Live stream for the first time.
It's fine.
It's good? Nice. Hey, Colleen.
Hello. I've got a big audience today.
Yeah, I know. We have a really high budget setup.
Oh, sweet.
I'm obviously being sponsored by some pretty powerful companies. We'll hang for a few minutes, let people log on. What do you think?
That's a big crazy.
Yeah.
Wow.
It's gonna be weird.
Yeah. Are you going home?
Right now, yes.
Yeah.
That's the plan. Right here.
Yeah, I'm taking a Flixbus up to Berkeley on the last day of our ride on the bus. Let's hope I don't miss.
Okay. My office mate right now is in our office with the same chair set up. He's got 2 chairs stacked on top of each other with the laptop on top. He's filming his own sections. Alrighty, well, we'll get going. Welcome everyone to the first ever live streamed Joe Green math discussion section. Like I said in my emails, I'm gonna do my best to walk over here and check for any questions. So if people on the internet are watching and you have questions, just type something in the chat, or if you can't read something, and I'll try to check it periodically and see what I can do. Otherwise, today we get to talk about a bunch of integration techniques, which has been the content of class for the last week or so. I haven't really had a chance to talk about integrals much this quarter with you guys, unless any of you were in section on Tuesday. So we'll see if we can run through a gauntlet of integrals today, talk about some of the new techniques we've learned, and go from there. Okay, the first one I want to do is the following. So this will be the integral of e to the square root of x dx. Okay, so I give this spiel a lot about a lot of different things in 31B. In particular, I talked about this a lot with infinite series, but the thing to keep in mind is that when you're practicing or when you're doing the homework, you open up the book to section 8.3 or whatever, and you know subconsciously you have a lot of contextual information about what technique you can use. On a test or on a practice test or whatever, you're going to get an integral like this, and you have no idea where it comes from. So it's always a good exercise to look at this and kind of run through all the techniques we have to see if we can figure out ourselves what to do. Okay, so here's my thought process when I look at this. In chapter 8, we've learned all these fancy techniques like integration by parts, partial fractions, trig sub, stuff like that. But before I jump to thinking about any of those complicated techniques, the first thing that I think to ask is there a simple substitution I can make? Is there an obvious composition of functions? I think there is in this case. So before I think about integrated by parts or anything like that, I identify, let me get so black marker. Okay. First thing that stands out to me is this composition of functions. So before I do anything, even if I can't quite figure out what's going to happen, I'm going to start out with the substitution for this expression. Okay. Now, another tricky thing that I'm going to do, and it doesn't really matter, it's not a big deal, but because I kind of know what's going to happen, in case we eventually have to integrate by parts, I'm not going to use the letter u. Just because when we do integration by parts, we do this u dv thing, and if I use u to do a substitution, I might get confused because u is going to mean the same thing, or it'll mean different things. So instead of doing a u substitution, I would start out with another variable substitution, t or s, star, smiley face, whatever you. I'll do a t substitution. And like I said, my gut tells me to do something like t equals the square root of x. Okay. As always, anytime you make a substitution, what do you have to do? You have to change everything. You have to change the function you're integrating, the differential, and then if we have bounds, those two. Fortunately, it's an indefinite integral here, so we don't have to worry about that. Okay, so dt, the derivative of the square root of x is like x to the 1/2 half. So the power rule says 1/2 x to the negative 1. That's going to be like 1 over 2x. And then depending on how you like to do u substitutions or t substitutions, you can think about solving for dx. And that's great and all, but we have a slight issue here in that what? I can't just plug this expression back in for dx because I'll still end up with an x going to. And that's enough. Every time you do a substitution, you want to turn everything to be in terms of variables. But let's start it off. So the integral that we're starting with is e to the root x dx. This is going to be e to x t. And then, like I said, the issue lies in dx right here. But this kind of thing is a little tricky, but it happens a lot. We can go back to the original substitution to figure out how to rewrite the differential in terms of the variable. So in particular, t is root x. What does that tell me about this expression? 2 times root x dt. That's just 2t. And that's good news because that I can plug into the integral, and now I have something entirely in terms of t. So here I'll get a 2t dt. Okay. So if I'm working on the problem, on the test or whatever, this is the first thing that I try to do. And then I stop and I reevaluate and I say, now what? The good thing about that substitution is now this is a pretty classic integration by parts. It's not, but you can think about it that way. And a lot of times if you have things being multiplied together, integration by parts is a pretty helpful technique. So that's what we have here. I think integration by parts is going to do a good job, so let's try it out. So let me remind you of the integration by parts. Integrating by parts says if you want to integrate something of the form u times dv, this is the same thing as u times v minus the integral of v. Okay. And the idea is anytime you use integration by parts, in order for this formula to be useful, you have to decide what you're going to call u and what you're going to call dv. In this case, it's not going to be so hard, but things can get a little tricky. So here's my general thought process for picking a u and dv. Usually I think about dv first. I think about dv first because whatever we call dv, we eventually need to figure out v. Right? What that means is we're going to, one, have to know how to integrate it. That's important because integrals are hard, and a lot of times we just don't know how to integrate something. And the other thing to keep in mind is that in general, when you do integration by parts, you're trying to make your life easier. You're not trying to introduce complication. So I think about which possible things I can integrate to not introduce unnecessary complication. What do I mean by that? To me, there's two natural candidates here. We have an e to the t and a 2t. If I were to call dv 2t, or t if I just ignore the constant, v would be something like t squared. And that's more complicated than the thing we're starting with. And that doesn't seem like a good idea. In contrast, what if I call dv e to the t? Well, then v is e to the t, which is not any more complicated than the thing I started with. So motivated by that, that seems like a better idea to me. So if you follow that thought process, if it were me, I would call dv e to t dt. Anything you call dv is a differential, so you need that dt. This is another one of these little picky things that people grading your tests are going to notice. It's not a huge deal, but if you can write these things correctly, it stands out. So dv is e to the t dt. That leaves only one choice for you, which is the other stuff, 2t. Okay. We need v, and we also need du. Du is pretty easy to find. If I take the derivative of both sides here, I'll get a 2 dt. And then e to the t, when we anti-differentiate that, we get e to the t. So v is e to the t. Now we're locked and loaded to run the integration by parts formula. So by integration by parts, this integral that we're starting with, e to the t times 2t dt, is, according to this, it'll be u times v. U is hiding right now, it's 2t. So I get 2t times e to the t. Minus the integral of v du. So v is e to the t. Du is 2 dt. Hope is that we've transformed this into something that we actually do know how to do. So the thing to keep in mind is that integrating by parts will never just give you the answer. It just transforms the integral into something new that hopefully is easier to do. And I think that is the case here because integrating 2 times e to the t all right. 1, 2, 3, 4, 5. So continuing from over there, that expression we can finish off evaluating 2t e to the t minus 2, the antiderivative of e to the t is e to the t. Throw in a plus c, and we've successfully done the integration. Are we done? Nope. We just plug back in our original substitution. So used to asking a gigantic group of people, are there any questions? But instead, I guess I will move to the chat. No questions. Hopefully everyone's doing well. The moral of a problem like this is a lot of times, even though the main technique being tested is integrating by parts, if you start off thinking like, oh, I need to integrate by parts, you could do it. But it's not as obvious, I think, to know what to do. So usually, if you can make a substitution, just a simple substitution, even if you're not quite sure how it works, that'll be a better option. All right. Let's see. biases. Okay, so next up, if any of you guys watching were in section on Tuesday, this is the same thing I did next, which is the antiderivative arc. So if you're watching and you saw me do this Tuesday, you can take a nap or something. Are we going to do the challenge problem? Probably not. You can talk to me about it some other time. Or I actually have the solution to the challenge problem on my website, if you want. I think it's under the challenging integrals document. Came from, so what am I supposed to do? Run through my options. Can I do any obvious algebra? Probably not. Is there a simple substitution I could make? I don't think so. There's not like an obvious composition like there was last time. Okay, then what's next? After algebra and after a substitution, I start thinking about chapter 8 techniques that we know, which are now integrating by parts, trig substitutions, that's 8.3, partial fractions. Is this a partial fractions problem? Almost certainly not. Partial fractions are designed for rational functions of polynomials. Definitely doesn't look like that. Is it a trig sub problem? It doesn't feel like it again, just because, think about the kind of trig sub problems we've done. They don't look like that. This is an inverse trig function, which is a different kind of piece. Okay, well, what are we down to? Integrating by parts again. Kind of by process of elimination, I arrive at integration by parts. Now, it seems a little weird because in the first example, I was talking about how, well, integration by parts you can think about as a product formula of some sort. But I only see one thing here. So it seems a little unnatural to do something like integration by parts, but it turns out that this is the thing to do. And I'll say this again, but anytime you have to anti-differentiate arc something, integration by parts is the way to go. The first time you see it, it's a little weird, but after you see an example like this, it's a pattern to pick up. So I'll write that down later. I'll make a comment. Okay, so I claim that I want to do integration by parts. I've still got the integration by parts formula there. As usual, we have to decide what we're going to call u, what we're going to call t. Okay, so again, this almost becomes a process of elimination type thing. Like I talked about before, whatever we call dv, it has to be something that we know how to integrate. So am I going to call dv arctangent? No, because that's the integral we're doing. I definitely don't know how to integrate arctangent. That's what we're trying to figure out. Okay, so I can't call dv arctangent, which means I don't really have a choice. I have to call dv 1 times dx. And that, to me, is what seems a little weird the first time I saw this. So dv equals dx leaves no choice. That means u has to be arctangent. And then let's run the formula, see what happens. Okay, so dv is dx. What does that tell us about v? Again, if you want, you could think about this as being something like 1 dx. When you anti-differentiate 1, you get x. So v is x. This part, another reason why this feels weird to me is because the other thing I was talking about over in this problem is that in general, you don't want to introduce complication. And we kind of lies in the face of the principle I was just talking about, but it's all going to work out. That's why this is kind of an interesting thing. All right, so then u, if u is arctangent, what is du? Now we have to remember the derivative of arctangent, which I probably talked about last week. I can't remember. But in case you've forgotten, the derivative of arctangent is 1 over 1 plus x squared. So u here is 1 over 1 plus x squared. So we'll run this formula and see what it gives us. What am I up to now? 5, 6, 7. I'm going to erase the formula. Or no, I can keep it. So integrating by parts, the integral we're starting with is arctangent of x. Integrating by parts says that we get u v, which might be a little hidden. Can't tell. Sorry if it is. U is arctangent. V is x. So this first term here is x times arctangent x. Minus the integral of v was x. Du is the thing that might be a little hidden, is 1 over 1 plus x squared dx. And that's where we are. And again, the hope is that this thing that we get is something that we actually do. Unfortunately, that's the case here. This can be done by a simple substitution in the denominator. If I call the denominator smiley face or d smiley face, two constants on top, and so this will be like a log. So let me finish that up. I'll let t be 1 plus x squared. And dt is 2x dx. So continuing from up there, we have the equals x arctangent of x minus, when I transform this latter integral with the substitution, I have a t in the denominator. X dx is 1/2 dt, so I can pop a 1/2 out front. Left with this, that's log of t. Done the integration, as usual, just have to plug back in for a substitution. Another one down. Silence is unnerving. Where did the 1/2 come from? So let me write that out explicitly. That came from when I did this substitution, dt is a 2x dx. So what I did in my head was I said x dx, if I divide by 2, is 1/2 dt. And then up here, I have exactly an x dx. So that turned into 1/2 dt, and 1/2 out front. Any other chat questions? Okay. Oh, what was I going to say? I was going to make some general remark, which I said on Tuesday, but I didn't really write down. Let me write it down. Mark, this is how you integrate arc anything. So I did this with arctangent, but if you have to find the antiderivative of arcsine, cosine, same way.
And then x is also done this way.
Yes, log of x is done this way because you probably shouldn't ever write this, but log of x, what is the logarithm? It's the inverse of e to the x. So one way to think about log of x is that it's arc e to the x. Don't ever write this, but that's what it means. So yeah, if you want to find the antiderivative of log of x, you would do exactly what we did here. You would integrate by parts by calling u log of x and dv dx. Turns out. All right. All right, so what do I do next? Let's do this. Another integral surprise. Sine to the fifth of x over secant squared. Secant squared. Like in my head, what is secant? I don't know what that means. It's 1 over cosine. So sometimes it's better to leave secants and tangents as secants and tangents, but a lot of times if you get confused when you see something like secant, it's not a bad idea to just take everything and rewrite it in terms of sine and cosine, because those things make a little more sense. So if it were me, probably the first thing I do here is I say, 1 over secant, that looks ridiculous. Let me rewrite that in terms of cosine. Secant is 1 over cosine, so this integral that we're starting with numbering the boards is a brand new feature that I'm starting to try out. As long as I can keep track of all the numbers. Numbers are hard. Okay, so like I said, the first thing I would do is I would use this fact about secant and then rewrite the original integral. Okay. Blurry screens. Uh-oh. All right. So 1 over secant squared would be cosine squared. So we could rewrite this as this. And this looks a little more tractable because in section 8.2 or whatever, we would Okay, so what's the game to win here? There's kind of two scenarios with these problems, and I'll remind you what they are. One of them is the good scenario, which is what's going to happen here. One of them is the less good scenario. The not as fun thing is sometimes you have to use reduction, which I'm not too hot when it happens. When do you have to use a reduction formula? If you have only even powers of sine and cosine, you don't really have much choice and you have to use reduction. That's the less fun scenario. Fortunately, we have an odd power of sine, so we can actually do something interesting. So I'll continue this thought bubble on the next one to describe what happens in general. The other scenario, which is the fun scenario, is if you have an odd power of one of these. So this will sound vague when I write it out, and then I think when we do it, it'll make a little more sense. But you pull off a copy of an odd power to pair with the differential to do a substitution. Okay, that made no sense. What do I mean by that? In the integral that we have here, here's what I'm going to do. So let me continue that string of inequalities. Cosine squared of x times sine to the fifth of x. Sine to the fifth is the same thing as sine to the fourth times sine of x. Point is, what I'm doing is I'm grouping one of these copies of sine with the dx because I'm gearing up to make a u substitution where I call u cosine x. If I eventually do that, if I call u cosine x, du is pretty much right. Now, I can't quite do that. I've got a couple of cosines here, but then I have a bunch of sines here. Fortunately, the thing that we can do is I can use my favorite trig identity to rewrite these powers of sine in terms of cosine. So I only know like 3 trig identities at most. One of them is cosine squared of x plus sine squared of x. So sine squared is 1 minus cosine squared. So the trick is sine to the fourth. This is the same thing as sine squared, quantity squared. And then I'll rewrite this sine squared using that trig identity. So then if I continue the equality from over there, this is equals, I've got cosine squared of x times quantity 1 minus cosine squared. Okay, so Billy asked, do you think we should be able to recognize other trig identities? Probably not, just speak well. So the test on the one hand is open book and open notes, and Marco gives you a formula. So I don't think you have to worry about memorizing any identities. Now, maybe that wasn't the question, and the question was like, should I be able to recognize when I need to use a double angle identity? Identities to be able to recognize are this identity. And then the next example I'm going to do is a trig substitution example. So probably the 1 plus tangent squared equals secant squared. I think if you have those ingrained in your brain, then you're probably in good shape. Mark says, thank me for being available. You're welcome, Mark. Okay. Now, like I said, it looks a little ridiculous, and it arguably looks worse than what we started with, but we're in good shape because I can make a u substitution if I've got dx or du. So I'm going to let u be cosine. Du in this case is a negative sine of x. And so what does this mess turn into? So continuing the equalities, I've got an integral of u squared, quantity 1 minus u squared, quantity squared. Sine of x dx is a negative du. Okay. It still looks a little ridiculous, but fortunately it's something that we can integrate. How do I integrate this? It's a polynomial. So unfortunately, we'll just have to multiply everything out, but then we have a bunch of powers of u. So let me do that. If you square this quantity, it'll be 1 minus 2u squared plus u. Distribute this stuff, u squared minus 2u to the 4th plus u to the 6th. Oh, yeah, good call. Thanks. I dropped the -7. Thank you. And then we're in the home stretch. 15. So antiderivative there is u cubed over 3 minus 2/5 u fifth plus u to the 7th over 7. Let's see. We've done the integration. Are we done? Nope. Just got to plug back in for u, which was cosine of x. And then yes.
If we were to take the parentheses out and make, like, how would the negative on the outside, we just change the signs?
Yeah, if you want, you could distribute. You could do like negative this plus this minus that. My laziness knows no bounds.
Can we do one question in the non-even part, not just the even powers?
Oh, can we do one?
Yeah.
Yeah, we can. So here's my plan, just so people watching know. Unless someone comes in here afterwards, which technically didn't have time to do on Tuesday. So stay tuned. Okay. Although I do need to prepare for my 32A section. 15. 15, 16. Okay, so like I said, the next thing I want to do is a trig substitution example. I'll do a slightly different one than I did on Tuesday, and then, so like I said out in my email last night, I uploaded a video of another trig substitution, so if you want another example, watch that video. The one I'll do today is what? I cooked up the integral of 1 over 4x squared plus 9, quantity to the 3 halves. Now, same deal as always. You know, I just started out by saying, we're going to do a trig sub problem. So you know that that's what's coming. But you open up the test, or I guess you put on the test on Tuesday, and you don't know where this came from. So you're going to have to figure out yourself that this is a trig sub. Now, if we consider some other options just for fun, could I do any algebra? No, that doesn't seem like a good idea. Is there an obvious composition of functions? I think there is. To me, there's like a blah, blah, blah to the 3 halves. So if there was a simple u substitution that would work, my gut would tell me to do something like 4x squared plus 9. If you want, you can try. But probably won't work just because the du in that case is going to be like a 2x. Then you'll have to figure out how to write that in terms of u, and it'll be gross, and it probably won't work. But if you want, but we thought about it. Okay, so then algebra substitution didn't work, so then I move on to my chapter 8 techniques. Do I integrate this by parts? You can try, but it doesn't feel like an integration by parts problem. Partial fractions, probably not, mostly because of this fractional power here. Partial fractions are really for rational functions, which means very specifically polynomials. Because this is like a blah, blah, blah to the 3 halves, it's not actually a polynomial in the body. So partial fractions may not be the best thing to do. So then where are we? It's not a power of sine, cosine, or something like that. So we ruled out all our other techniques, and we arrived at trig substitution. Okay, so what's the idea behind a trig substitution? The idea to me, identities to my advantage to simplify this expression. So like I said, I only remember a couple of trig identities. One of them I wrote down earlier, and the other one, which is really the same trig, is if you take this expression and divide through by cosine squared, you get 1 plus tangent squared. And then 1 over cosine squared is secant squared. What's the point? I want to think about these, and then I look at this, and this is a vague question, but this is kind of the thing that you have to ask. Or, okay, so this whole weird final format is kind of interesting. So I guess if you're watching this and you're taking the final on Tuesday, you can open up the book, and the book tells you what kind of substitution to make. But that's kind of boring. So what's the point, or where does that substitution come from? You look at this and you ask, how does this make me feel? Or which one of these trig identities does this make me feel? I see something squared plus a constant. Here, This one, I see something squared plus. Now the constants are a little wonky, right? I've got a 4 and a 9 here. This is just like 1 plus tangent squared. But roughly, the structure of this expression in the denominator mimics the structure of this expression. So what I'm thinking right now is I want to use this trig identity to simplify this expression. In particular, I want to rewrite this thing right here to look like this. That's my goal in the trig section. So there's a number of ways that you can arrive at the correct substitution, and however you want to think about it is totally fine. I did a thought process like this in some previous problems from maybe last week, but I take the integral that we're starting with. And then I look at this trig identity, and I see a 1 here, and I think, man, I really wish this 9 was a 1. That'd be great. Well, how can I make that happen? I could just factor out a 9. So if I factor out a 9, I'll pull the 9 through the parentheses. When I pull the 9 through the parentheses, it'll pick up a power of 3 halves. What am I left with? I pulled out a 9 here, so this is like plus 1. And then I pulled out a 9 from 4x squared. What does that leave me with? 4x squared divided by 9. So that's the first step I would do. And then I have a 1 here now. And then I think, man, I really wish that quantity in the parentheses looked like 1 plus tangent squared theta. Because if it did, I could use this identity to simplify things a lot. So let me write that down. I'm looking at this and I'm thinking, man, I really wish this looked like 1 plus tangent squared. So I really want this thing to look like tangent squared. If only. Well, how can I make that happen? I can just speak it into existence, or I can write it into existence. That's what a variable substitution is. I just declare this to happen. In particular, if I solve for x here, take a square root and move the constants to the other side, this would tell me that I really want x to be 3 halves tangent. So this came from just taking the square roots of both sides. You get like a 2 over 3x equals tangent theta, and then 2 over 3 to the other side. Let x be this. Okay. Now, to me, the first time I saw something like this, it felt a little weird. And my inclination is like, am I allowed to do this? Like, can I just call x 3 halves tangent theta? Yeah, you can do whatever you want. You can call anything else. It's just a substitution as long as you correctly change everything in the integral. If you do that, so just like any other substitution, we have to rewrite not only the thing we're integrating, but we also have to rewrite the differential. Dx, if x is 3 halves tangent theta, is is 3/2 the derivative of tangent secant squared. All right, so what happens? This integral turns into, so that 9 to the 3/2, let me pull that up. 9 to the 3/2, I'll say this out loud, and if it's confusing, you can let me know. 9 to the 3/2 is 9 to the 1/2 to the third. So that's the square root of 9 cubed, which is 3 cubed, which is 27. So this is 1/27. Integral 1/, blah, 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 plus 1 to the 3/2. By construction, 4x squared plus 9, after we make this substitution, turns into tangent squared. We rigged it up somehow. And then dx, which is right here, turns into 3/2 secant squared. Common theme doesn't look a whole lot better than the thing we started with. How are questions doing? So far, so good. But the other common theme about math is what can we do here? We can do a whole lot of algebra. In particular, the main reason why we're doing this is because here we have a 1 plus tangent squared, 1 plus tangent squared. That was the point of everything I'm doing. I can rewrite this as, so let me pull out some constants again. 3/27 is 1/9. 1/9 times 1/2 is probably 1/18. I may have done that right. Secant squared on top, and then like I said here, tangent squared plus 1 is exactly secant squared. So I have secant squared quantity to the 3/2. Okay, and it's looking better. Here we have a bunch of powers of secant that we can. I'll take an over under for how many boys I use up to 19. So let's simplify all those secants. I have 2 of them on top, and then in the denominator, secant squared to the 3/2. This is the same thing as secant to the 2 times 3/2. Which is secant to the third. So that's how that simplifies. Does pulling out the 9 to the 3/2 not change the power of 4 times x squared? So it kind of did, I think. So when I factored out the 9 here, I definitely did change this term. You definitely do have to account for it. You definitely do have to account for this term, but nothing up here changes. It's just a matter of dividing through by 9. So if this is a little confusing, if you want, you can redistribute this expression in here, and you should end up with something like this. So this is definitely correct. You can think about it yourself if you want. And the other thing that I said earlier is you don't necessarily have to do exactly what I'm doing here. Your end goal in a trig sum like this is to arrive here. So if you can get this, you're in good shape. So if you open up the book and you some table will probably tell you to do this. So maybe on an exam you don't have to worry about it. So the other question was, where does the 1/18 go? Good question. Thanks. I don't know. I got tired of listening to me do that, so we left the discussion. All right, so secant squared over secant cubed is 1 over secant, which is cosine. And thank God that's something we know how to integrate. Oops. The antiderivative of cosine is probably sine. Tack on plus c. We've done the integral. Are we finished? No. So yeah, good expression, or good question is in the textbook, it says that you want to do a trig substitution when you see like a square root of blah, blah, blah expression. And the question is, we don't really have that here. So am I still allowed to do a trig sub? There's a couple answers to that question, one of which is you can do a trig sub anytime you want. Let's say you got the integral of x. If you wanted to, you could do a trig sub. It would be a little silly, but the good thing about a variable substitution is you can do it anytime you want. Now, the next question is like, is it useful to do it if I don't see a square root? One answer to this question would be, there is actually kind of a square root hiding here. Let me make that clear. This expression over inside the integral, if I wanted to, I could rewrite as 4x squared plus 9 quantity cubed. That makes sense. So there actually is kind of a square root expression here, and it's hiding a little bit. But to me, that's not even really the point. And for anyone who is in section on Tuesday, I did an integral where it was just like some stuff squared in the denominator, and there was no square root, and it wasn't even hidden. So to me, it's not the square root that's important. It's really the 4x squared plus 9 term that matters. And then it kind of doesn't really matter what's happening around that. That's a good question. Okay. Oh, where are we? Oh yeah, we did the integration, and then my question was, are we done? The answer is no. As always, we have to go back to x. The one of the many tricky things about a trig substitution is this process. Normally, when you do a u substitution, going back to x is just a simple matter of plugging in for you. Here it's less straightforward because the thing that we ended up with is sine of theta. But then if I go back to the original substitution, we have something proper. X is 3/2 tangent theta. How do I go back to x? This is the best way to do it. It takes a little bit. What I'm going to do is I'm going to interpret my original substitution on a right triangle. Okay, so the original substitution is here. Let me rewrite this a little bit. I'm going to solve for tangent theta. So the original substitution was tangent of theta. Let's go back to high school. What does this mean on a triangle? SOHCAHTOA. Tangent is the opposite over the adjacent. words, if I drew a triangle, right triangle, angle theta, tangent of theta is this side divided by this side. Opposite, adjacent. Tells me that the opposite side here is 2x, the adjacent side is 3. Then I can use the Pythagorean theorem to solve for this side. Pythagorean theorem says this, the hypotenuse is this squared plus this squared. So we get that. And what's the point? What are we trying to rewrite? Sine of theta. But sine of theta is so it's the opposite of the hypotenuse. So sine of theta is this. So let me finish this off. Over somewhere. Okay, so to conclude, this thing that we started with is 118. Sine of theta was 2x over root 4x plus 9. 4x squared plus 9. See? There we go. That's a trig sum problem. Okay.
So, you know how you said that the constant and a square changes, so we should use one for tan square. What do you do if you want to pick? Would there be like a squared, two squared numbers for cos square cosine? Would it be 1 minus?
Oh, so yeah. So in the situation that you'd want to use the first trig identity, the cosine squared plus sine squared, the kind of thing you're on the lookout for is if you have something that looks like 1 minus something squared, then you say, if I call the something squared cosine squared or sine squared, then you can use that identity. Yeah, good question.
You can choose which one to use, sine square.
Yep. Okay. Let me do a reduction problem formula really quick, and then we'll call it a day there. My voice needs a little bit of a break before another like 5 hours of streaming today. Okay, so earlier I was talking about how when you have powers of trig functions, there's kind of 2 scenarios. One of which is you have an odd power of either sine or cosine, or maybe both. And you can pick off one of the copies to pair with the differential, rewrite everything else using trig identities, and then do a trig sum. The part where you can't do that, the kind where you can't do that, is when you have only even powers of sine and cosine. So, just for example, what if we were handed the integral of sine to the 4th x? I look at this, I think even powers of sine of x, I probably need to use a reduction. Now, here's where you guys might have to. I joke a lot about how, like, oh, I only know 2 trig identities or something. I could probably give you 5, maybe. But I genuinely don't remember the reduction formulas. I don't have time to do that. So I genuinely don't know what the reduction formula for sine is. If you wanted me to, I could figure it out. But let's just take it from somewhere. So the reduction formula for sine of x is probably something like if you integrate sine to the x dx, this will give you 1 over n sine to the n minus 1 x cosine of x. Do any of you guys have it?
Yeah.
So, I don't know.
Plus 9 and
Is this part right?
I think so. It's like n
Minus
So it's probably almost this.
there's a
n minus 1 by n. Like
Over here?
before the integration.
Did I get this part right
And
though?
that's minus 1 by n.
Okay.
That's cool.
Now, after you watch me just fumble trying to figure out a reduction formula, like I said, I myself don't have the reduction formulas memorized, because you'll get a formula sheet and because the test is going to be open book and open note and stuff, you won't have to memorize a reduction formula. But one thing I would be able to do, and I mentioned this on Tuesday for anyone listening, you should be able to show where this comes from. I don't want to do that now because I'm kind of tired and we're a little out of time, but during a review session or something, I'll go over where these formulas come from. It's a good idea to be able to do that. For a problem like this, fortunately, you just have to be able to open the book or check the formula sheet and use the correct reduction formula. So the example I'm going to do is just demonstrating how to use one of these reduction formulas. So what's the point? The point is that we're trying to figure out the integral of sine. So I want to integrate sine to the fourth. I'm going to let the reduction formula do all the hard work for me. So I would say by the reduction formula, the integral of sine to the fourth is up here. I'm going to just spit up this formula in the case when n is 4. So if n is 4, what does the right-hand side say? It says -1 over 4. Sine to the 4 minus 1 is 3. Cosine of x plus 4 minus 1 is 3 over 4. Integral of sine squared. So just like integration by parts, the reduction formula is integrating by parts. It doesn't give you the answer, it just turns the integral into a new integral. So I get here a sine squared, and then I say, now what? We could just use the reduction formula. So what do I mean by that? Plus 3/4 quantity. What I'm going to do, and there are other ways you could do this. You could use like the double angle identity to evaluate this, but since we're using the reduction formula, I can spit up the reduction formula on this thing, now using n equals 2. So when n equals 2, what does that thing say? It says -1 over 2 sine to the 1 x cosine x plus 1 over 2 times the integral of sine to the 2 minus 2 is sine to the 0, which is just 1. After applying the reduction formula twice, I've taken the sine to the fourth and I've knocked it down 2 levels to something that I finally do know how to anti-differentiate. The antiderivative here is just x. I think that's a record for this discussion section. I go over like how you actually prove one of these reduction formulas, because I think that's a good thing to be able to do. Okay. Signing off. Goodbye, internet. This video should go up on the YouTube channel as a regular video, so if you want to rewatch it or whatever, you can do that. Otherwise, until next time. All right, give me 1 sec. I don't know how this works. End stream.